Hi everybody, welcome to yet another lecture. Today we're going to talk about MapReduce, which is going to be fun and totally unrelated to everything we talked about before. So in case you got lost, you can start anew with this lecture. First announcement, homework 5 will be online tonight. I have one more stage of proofreading and then it's going to come out. And Stephanie was so great to do a first visualizations of our prediction contest. So these are the polls you all came up with, the results. So we have here anonymized our CS109 students, and these are the predictions you made for the number of Republican senators. And we have the New York Times prediction and Nate Silver and Sam Wang here for comparison. What?
There's a couple of people who are mathematically eliminated.
Yeah, there are a couple of people who were mathematically eliminated. So we were basically saying that prediction is so much off.
Not that. That would be, so look, if you, the person who did.
Wait.
If you did, this is now price is right stuff. It's not really statistics. Oh, yeah. So if you look at there's someone that did 51 to 52. That person is eliminated because somebody did 51 only, and another one did 52 only. So, sorry. I guess that's all. Oh, and then there's another little point. Another thing I wanted to point out, just so you're aware. There's no reason to include decimals, right? Because you're just making your interval bigger. There's not going to be half a Republican. Anyways, but that was just a minor little detail that I think most of you caught, because you can see most everybody has integers, but there's a couple that have decimals. Anyways, that's not a big deal. But the good news is that we might have someone beat the big boys, whatever you want to call them, and then we can claim that this was the only entry and write a letter to the New York Times.
And this is how you do data science. See, after data wrangling, we only had one valid entry, and that was the one. Okay, yeah, but in total, I think this is cool work. So today, as I said, we're going to talk a bit more about object-oriented Python, simply because the library we use for MapReduce is going to be object-oriented, and you need to inherit from that class. So I'm going to give you a very brief introduction into what that means and how you do that. And then we're going to talk about MapReduce and design patterns, and how you can maybe use this in your final projects. So if you want to learn more about this framework, I really highly recommend this book. It's focusing on text processing. So it's data-intensive text processing with MapReduce. But I think it's the greatest introduction out there, and it's going to show you all the basics. And it's free. So if you go to that URL, you can download the book and read it. And there are also online lectures from Jimmy Lin available, and he's cool in explaining this. And the book goes much deeper than what I am going to talk about. Like, I'm going to give you the introduction, workflow, and if you really want to dive into the material, you can read that book. So what is MapReduce? MapReduce is a programming model, and that also means it's a way of thinking. It's like if you switch from imperative programming, and then you're using functions, right? And then maybe you're switching to object-oriented programming. You start to think differently because you're expressing your thoughts in a different way. You structure your programs in a different way. And MapReduce is a framework that is addressing large data sets, and it's a parallel and distributed framework. But it is making using parallel and distributed computing very simple. And this is why it had such great success. You're going to see there's a lot of things normally you need to take into account if you want to use a parallel framework. Like anybody who's been taking CS205 knows that there's a lot of communication between different clients. You need to take care of what happens if one of the nodes of the cluster just has a failure, and you need to restart a job. All of these things the MapReduce framework takes care about. It's all behind the scenes. And you sit in the comfort zone and only can write the functions you actually care about. So it's a cluster framework, and you need to start to think in terms of map and reduce to program in this framework. And just a bit of background, originally this was developed by Google for their large server infrastructures. And then Apache wrote Hadoop, and that's an open source implementation in Java. And we're going to talk about Mr. Job or MapReduce job. I know I just say Mr. Job. And that's a Python interface that uses Hadoop. So if you really dive into Mr. Job, you're going to see that it actually can call Java functions in the Hadoop framework. We're not going to go that deep into the material, but just so you know, there's still, normally if you address an actual cluster, there's still this Hadoop running in the background. This is what you're using. And Mr. Job is providing you with an interface. But the good news is you can use Mr. Job just on your computer. So in Homework 0, we ask you to install the library. And if you want to try MapReduce things, you do not need a cluster at all. The things I'm going to show you today, the examples are so small that there is no problem just using your personal computers, your laptops even. The only difference is then you won't have real parallel computation, right? Your laptop is going to simulate that, but it's going to compute one thing after the other. But you can still write MapReduce programs and see whether they run or not. So there's going to be a map step. And that is a form of filtering and sorting. And then you have a reduce job that is a summary operation. So what does that mean? This is a graphical explanation. So all your data is going to live somehow in the cluster. Even if it's too large to fit on one hard drive even, you don't have to take care about this at all. You can just think about your data living in a cloud-like thing somewhere in your cluster. And you are going to write a map function. And what this map function does, it takes key value pairs. So the whole MapReduce framework assumes that your data comes in key value pairs. And then you write a function that takes the key value pairs, and outputs key value pairs. And in this example here, just outputs single letters and a number associated with each of these letters. And you only write one map function, and the MapReduce framework distributes this and decides how many nodes it's going to use and how they run in parallel. So all of this, you just take care about this map function, about one of those. So the output you can see here, this first one, for example, outputs an A1 pair. And then the third one here also outputs an A key, but this one has the value 5. And then there's the shuffle and sort. And the good news is also that is a step you do not need to worry about. This is, again, something the MapReduce framework just takes care of automatically. So what it does is it collects all the different key value pairs from all the mappers and shuffles them and sorts them. So then afterwards, you have the A key, and you have all the values that any of those mappers generated for that key. Right? So this A1 came from this mapper, and A5 came from this mapper, and after the shuffle and sort, I have here a list that says, to the key A, I got 2 values, 1 and 5. And these are then distributed to the reducers. And this is the second step you actually are implementing. So you implement the map, and you implement the reduce, and what the reduce should do is it just looks at this key and the list, and then it assembles this into whatever summary statistics you want. For example, this could be a sum, right? So the reducer here could look and say, A, in total values, I got 6 for the letter A. And then would output this. So, and this is the hello world of MapReduce. It's word counting. So whenever you see an introduction to MapReduce, this is what you're going to see. And this is where the object-oriented programming comes in. You see here, we just import the Mr. Job framework. And now here we define a class. And you've actually used classes before when you used scikit-learn. Remember, like we had a classifier, and you would call classifier.fit, classifier.predict. And that fit and predict was a function of that classifier. And that classifier variable also magically knew whether it was already trained or not, right? Like calling predict before the fit didn't really make sense. But once you called the fit on whatever training data, you could call the predict function just with any new unseen data. You didn't need to provide the training data again. So apparently the classifier variable somehow internally kept track of what it had been trained to do, what it had learned. So and here now we have a Mr. Job class. And this Mr. Job class you can think about just has this whole framework somewhere in the background. You don't need to worry about it. You just inherit from that one. And here you can see you define a mapper function and this reducer. So this is what it looks like. You just define these two functions that correspond to this map step and this reduce step, and that's all. And when I first saw this, I thought it's really, truly amazing. Because if you've ever considered doing parallel programming, it is a lot of hassle, and it is a lot of low-level thinking about communication, message passing, and you don't need to take care of any of this here. So object-oriented programming. I just wanted to do an example. So this is now a class that I defined. And it's very simple. It's called box. So I have a class called box, and you see this init function here. And what it does is, when I very first create a variable of that type, I create an actual variable and say it is a box, then this function is going to be called this init. And this is going to set an internal variable, number of objects, and that is 0. So when I create a box, it's empty. Who has already seen this object-oriented programming in classes? Wow. OK. Then I'm going to go faster to not bore 90% of the people here. So this is called in the beginning. Then I have an empty function. You can put objects in and print the number of objects. And like with scikit-learn, you can create a variable now. And if I do tab completion, you can see it has all these different functions. So I'm just going to go over inheritance briefly. So now if I want to extend this and say I want a class labeled box, I can do what we did with the Mr. Job class. I now define a class labeled box and inherit. You see this says box now. So this is going to be a box. It's going to have all the functions I defined for the box before. And in addition, it's going to have this function print label. This is all I'm saying here. And then there's the super function that is going to call the init from the actual box. So this super function kind of makes it a box, and then I have additional stuff going on. So you can see now box A was the box before, and box L is now a labeled box and has all the functions from box A, even though I didn't define them, and has the additional attribute label and the function print label. So and what we're actually doing with the Mr. Job class is we're writing over a function it already had. We're redefining the mapper and the reducer. This is how this framework works. So with the labeled box, this means if I want to have this print number of objects was a function that the original simple box had. And now I say the labeled box has the same function. It's the same name. But it actually outputs not only the number of objects, but also the label. So it gets a different name. What you can see now is box A was the simple box, and I use this function. And it says box contains 5 objects. And box L is a labeled box, and I call the same function. This is the same name, but the output is different. And this is because I said box L is also a normal box, but do not use the print number of objects function from the normal box, use this one, right? So I wrote a new one, and that is shadowing the old one. The old one is not accessible from this labeled box. And this is exactly what is happening here. You inherit from a Mr. Job class, and you do not care about all the stuff that is defined in that class. It comes for free. This is all the stuff that the library does for you. And all you do is you redefine the mapper and the reducer here. So this is why you only need to write so little code, and it will run. Because this is literally everything that is in that file. This is the only Python code you write to do a word count over I don't know how many documents. And this is something you haven't seen because we used IPython notebooks in this class so far. This says if this script here, if you just save this to a file .py, this says if this is executed from the command line, then just run MapReduce word count. And that is my class up here. And this run function comes from the Mr. Job class. Other questions for this? I skipped over this more faster because so many people seem to already know it. Yeah? Yeah? Can you explain what mapping is? Yes, this is what the lecture is actually going to be about. It's going to come. Yeah. But the actual syntax is clear. So you define this class, you override these functions. This is how this works, because otherwise this file looks somehow incomplete, and it's like magic, that I can run this and it's actually already doing something. It's not only doing something, it's running a program on a whole cluster if you want. So there's one other thing that is this yield keyword here. And this looks weird. Yield is in Python for generators. So what that is I can define a function and say, give me the first numbers until n. This is what this function here does. It has an empty list nums, and the actual number it is at the moment. Then there's a while loop, and it increases num. And as long as num is smaller than n, I keep increasing it and appending it into one long list. So I'm generating the whole list of numbers until n. And now let's say what I'm actually interested in is the sum of the first n numbers. Why is this really bad coding, what I did here? Yes. I don't need to store all these numbers. What I'm doing here is I'm actually generating the gigantic list only to add them all up, right? So at one point, I have this gigantic object in my memory that I actually didn't really need. I only needed one number at a time. And this is exactly what a generator does. So now I have the same idea, but instead of actually generating this whole list, I use this yield keyword. And what this is going to do now, it's going to generate a 1 and a 2 and a 3 each time it is queried. And now when I want to sum the first n, this goes over this function. It's just giving me one number after the other. It's not creating this whole long list in memory. And just as a note, in the normal 2.x, I think in 3 it's only generators, but we are using 2.7. So if you just use range in a for loop, it's actually going to generate that gigantic list. And if you use xrange instead, it's going to use a generator. So if you run out of memory or have a really long for loop, this is how you can save space. Yes? The question is, what is the difference between yielding the numbers and just generating x is x plus 1? Oh, OK. I think what the question means is, so the exercise here had the sum outside of the function. So this was not keeping track of the x. Yes, there are other efficient ways to sum up the first n numbers and not like take the whole list. It was a bit of a example generated here, but yes. The whole idea here is that you have the sum outside of the function, but we never ever cared about having all those numbers. So this just gives me one number at a time, and I can add them up. So this is just the original mapper function in Mr. Job is a generator. This is why you need this yield keyword. So it just needs to be in there when you define your own mappers. So this is the word count example now applied. So green eggs and ham. Who knows that book? Ah, that's less than I thought. So I actually came here and in the first year, and I didn't know it. And I've never heard of it. But it's the 4th best-selling English language children's hardcover book of all time. I wonder what it is when you remove that hardcover. But the story is cute because it's a children's book, and this Dr. Seuss has written also The Cat with the Hat or something. So he's famous, basically, in English-speaking countries with children. And this book was the result of a bet. He had just written a bestseller, and his editor said, publisher said, you can't write a book with only 50 words. And he accepted the bet and wrote this bestseller. And we can verify that it's indeed only 50 words. So this is the text. I am Sam, Sam I am. That's Sam I am, that's Sam I am. I do not like that, I do not like that, Sam I am. Do you like green eggs and ham? So I read on Wikipedia, I actually needed an interpretation of this book. I read that Sam I am is supposed to be a name of a person, and this is a dialogue between them. And he's trying to persuade that other person to eat green eggs and ham. And he's always rejecting this and saying, no, I don't like them, and he doesn't like them in a lot of locations. And in the end, I think he actually tries it and likes it or something. That is the whole book summary. But now, if we want to verify the bet, this is what it would look like. So we have our word count example here. And this mapper is automatically, this is going to happen automatically in the background. What you can assume is MapReduce goes over this text, and it's going to read it line by line. And what the mapper input is an unknown key, I think it's just a number or something, and then this line from the text. So the first, if we do this sequentially, the first mapper input is going to be I am Sam. So this is what this mapper here gets. This is the line. And now we say for word in line split at the space, right? So this split gives me the single words in that line. And now I say for every word in that line, I yield the word in lowercase letters and a 1. So what this means is the word is going to be the key, and the 1 is going to be the value that the mapper outputs, right? Remember, the mapper gets data in key value pairs and outputs data in key value pairs. This is now a different type of thinking that is coming in. This is something you just get used to if you use this framework over and over again. So I am Sam. First output is going to be I in lowercase and a 1. And then it's going to output am lowercase and 1. And Sam lowercase and 1. And then it's finished with this one line. It's going to get the next line, which is empty, and then all over again. And now what this MapReduce is doing in the background is there's not only one mapper, but there can be 100, right? And then each of those gets a line and is outputting all these key value pairs. You can see it's going to be a lot of key value pairs. Every word in the text is going to be one key value pair, with the key being the word and the value being just 1. So what the 1 then does, then comes this sorting and reshuffling period, right, in the MapReduce framework. This is, again, done for you. So the output then would be, let's take Sam. So somewhere in the output here in between, in the shuffling period and sorting, I'm going to get an array now, or a list, that has Sam and then a 1 for every time it occurred in the text. Right? Because the mapper, every time Sam was in this text, it would output Sam and 1. And in the sorting period, now I get all the values aggregated for the single key. Right? So Sam was the key, so I get Sam 1, 1, 1, 1, as many ones as it was in the text. So then we call the reducer now, and the reducer gets this word, Sam, and all the occurrences. This is this list with all the ones. All the different values that were given for this one key. So all it needs to do is to sum them up, right? Because I get them all. So now I just say, I keep the word, that was the key I got in the first place, and now I just sum all those ones up that I got, and this gives me my word count. Is that clear how that works? Yes? Oh, what does self do is the question. This is also due to this object-oriented programming. This just says this is a function of this class, and self is referring to that actual object that you created. If you did not understand what I just said, just always put it in there. Yeah, it's just every time you have a class and you define functions that are inside the class, right? You see this indent here? Like, this is a function that you can call afterwards with mr.wordCount.mapper, right? Like here, we don't see this actual run function because it's inherited, but you could write mr.wordCount.mapper and it would give you that function. And for that to work, it needs to know this object here, and this it gets over the self. So if you don't get that, what I did for the first 2 years, I used Python. I was just like, okay, I'm defining functions inside a class, so the first parameter is always self. Yes? The question was whether for the reducer, the key is always what I output here, and the value is always going to be a list. Yes. The list, the value here, the occurrences, is always going to be a list of all the values that the mappers produced for that key. Yes. Yes?
Sorry, just to clarify, so does self mean that you can call it outside of, outside of that class? Or?
Does self mean you can call the function outside of the class? You mean as a static function?
Like you said, you could do mr.wordCount.mapper.
Yes.
So if you didn't have self, you would not have done that.
The question was, you said you can do mr.wordCount.mapper. Without the self, you could not do that. No, it would complain that there is an argument missing. Like if you use, at least I believe that would work that way. I'd have to try that. Because I think I just tried to read this up more clearly, and I think this is not a keyword. You could redefine this somehow. But this is, for Java or C, I think this would be the this. So it refers to the actual object that is created by the class. Okay. So this is literally what you would have to put in a Python script to run this whole word count thing on the cluster. And the reason this is so short and convenient is that the MapReduce framework does all the complicated work for you in the background. So this is how you would actually launch the job. So you would call Python, right? This is how you would launch any script on the command line. You would call Python and then myscript.py. This is what you would normally do. And if this now is a MapReduce job, what you do is you put this input file here, and these here, these square brackets you actually need. Those are pipe symbols. Like this is putting the input file, basically the text of that input file, into the script. And then the output file actually gets the output from the MapReduce job out. So this is not me trying to emphasize this input file.txt. These are actually characters that you need to type. Well, that's it. So this is what an output file then looks like. So it's 50 words in total. I omitted this first square space count. And then you have all the different words here. These are the keys, right? Remember, our words were the keys. Also, the reducer outputs the keys here again, the word, and then the sum of all the occurrences. And this is exactly just the list then in our output file. So what I get is the list of all the words in the text and how often they occur. And this is just an example why this actually could be useful and fun. There's a cool TED talk about culturomics is what they called it. So you can go to this Google Books Ngram viewer. What they did is Google Books has archived thousands, I believe, of books over the centuries even. And what they did is they used word counts. And what you can output is the number, the frequency of the words over the years in all the texts that Google has. And what you can see here, for example, I did war. And there have been 2 periods here in recent history where people were very, very interested and had a lot of reports about wars. And when you look at the years, it's not that surprising, right? So our world wars created a lot of news traffic. Then I wanted to do something more fun. So if you do the same thing with Apple, you can see that people were moderately interested in their nutrition beginning in the early 1900s, and then they got really, really health conscious somewhere in the 80s, right? So this is kind of a culturomics, maybe not failure example, but it shows that you need to take care with interpreting the results. But still, it's fun and it's cool. And you can try different words yourself, and you can also plot one word against the other.
Try tweet.
Huh? To eat? Tweet. Oh, okay. Yeah, I haven't. I don't have it online here, but the URL is here, so you can try it yourself. So another simple example, just to get into this mode of thinking, is an anagram finder. So anagrams are words or phrases that consist of the same letters. So you take a favorably long word and you scramble the letters and you try to find something else that is also meaningful. And I found a web page with examples, and they said an anagram of dormitory is dirty room, of astronomer is moon starer, and of election results it's lies, let's recount. I like that one, like with the homeworks and everything. So yes, the web page has some more fun examples there. So if you want to verify anagrams with MapReduce, right? Like it's cumbersome to do this manually. Like I would, okay, this M is taken here, and now I have the 2 O's, okay, right? But you could write a MapReduce program that just goes over thousands of words and tells you which ones are anagrams of each other. So we want to verify anagrams with MapReduce, and our input is just 1 word per line. And this is the program, what it can look like. So here you have the mapper, and we don't care about the actual key in the beginning because we said in Mr. Job, it's just 1 line, right? The framework just gives you 1 line of your text file at a time. In this example, 1 line is just 1 word. And in the mapper here, this now converts the line into a list of the actual letters, and then we sort those letters, and the output is the letters as the key and then the actual line. Why is this a good idea to choose the key as the sorted letters of the anagram? What is happening here? Yes?
That way, all of the things that are the same, like something that's an anagram of another, then will have the same key.
Yes, exactly. So if we do this, all the anagrams, all words that are anagrams of each other are going to have the same key. It's a canonical representation of the word. It's just the alphabetical sorting of all the letters. So all the anagrams, all the words that are anagrams of each other are going to have the same representation. So I can now yield this key, just the letters, and then the line is the actual word. And then in the reducer, it's going to get all the words that belong to the same key. And I actually don't care really about the letters, right? That canonical representation most probably is useless. Like it's not an actual word. So what we do here is we go through all the words in this list that we get here and append it together to the anagrams. And we say if this is longer than 1, then we yield the actual anagrams and how many there are. So this is what we said. We have our map step. We have the single key value pairs generated, and we have the sorting. and then we go to the reduce. Now let's make this more efficient. So of course it goes a bit further than this. So if you think about how you would like a cluster to scale, right? If you have more data, or if I tell you, oh, I got new money, my cluster is twice as big now. So what you ideally would like is, if you have twice the data, you only have twice the running time. And if I give you twice the resources, you only have half the running time. This is what you normally would like to have. But normally you can't achieve this, or it's at least very hard to achieve. And the reason is that you need to synchronize, and that requires communication. Even if the MapReduce framework does that in the background for you, you can imagine if you use twice the number of mappers, right? You still need to take care that every one of these has finished so that the sort and shuffling phase can aggregate all the values. So all this communication in the background takes time. So one idea is we want to avoid communication. In MapReduce, that means we want to avoid emitting too many key value pairs, because these cause a lot of the communication in the framework. And there are two possibilities. One is to use combiners, and the other one is to use in-mapper combining. And this can make your code really, really more efficient. So what we do now is, after the map, we introduce this combiner here. And you can think of a combiner as a form of mini reducer. So what's it going to do is, here, if the reducer was actually summing up the values, we already do this in a step before here. So this combiner here already takes the C3 and C6 and combines them into C9 and outputs this. So this, because this is running on the same node now, before this actual shuffle and sort phase, this is reduced communication, because this combiner takes only care of this one mapper. You can see here it doesn't see the C that is output by this mapper. It also doesn't care about it. This combiner only takes care of the one mapper it is attached to, kind of. So you can think of a combiner as a form of mini reducer, and this can significantly reduce the network traffic. But, and these are the important parts here, you don't have access to the other mappers. I said this guy here is not going to see the C2 generated by the other mapper. So you cannot rely on actually having all the key value pairs out there. You only see a subset. And you are not guaranteed to run at all. And this is another very important requirement. Like when you program, you need to take care that you're not relying on the combiner and on its output, because it might not run. I think what is happening in the background is, if this guy is very fast and this guy is very slow in outputting the key value pairs, the MapReduce framework has time to run this combiner here, right? Because this is fast and he already finished. And then you can run the combiner, whereas if this guy was really slow for whatever reason, right, then you maybe don't have time to run this combiner, and it's better to just start the shuffle and sort. So you cannot rely on this combiner actually running at all. And the key and value output must match the mapper. Why? The output of the combiner needs to be the same as the output of the mapper. Oops, sorry. Yes, exactly. There's no guarantee that it will run. Right? So you cannot change the signature of the data. Whatever the output of the mapper is, needs to be the output of the combiner. So now the same word count, but we use a combiner here. So what we do is we have the mapper, and put out all these key value pairs, the word itself, and then a 1. And now you see the combiner is just an exact copy of the reducer. Just really the same. Just takes the words and sums up all the occurrences. Oops. So combiners and reducers share the same method signature, and you often can just take the reducer and make it a mini combiner for that mapper. But that doesn't work always. Because the important part is always to keep in mind that the combiner might not actually run. Or it can even run multiple times, like if there's a lot of time to spare. So this is an example in pseudocode where Jimmy Lin is computing the mean of a data set. So you have your class here, the mapper, and this is your mapper function here. And you can see it gets this key, a string, and this value, an integer. This is your key value pair. And then it's emitting a key value pair. And then in the reducer, you now have the sum and the count. And for all the integers in that list that you got, this is all the lists of the values associated with your key. You sum them up, and you count how many there were, and then you compute the average. Yeah? So I said the simplest version is to just take this reducer and copy, paste it, and put combiner up here. Like substitute this reducer with a combiner, and then you can run it. In this example, we can't really do that. Why not? Yes, the average of averages is not necessarily the average of all the numbers. Right? So what would happen is I would maybe already compute some averages of numbers from a mapper, and then when I run the actual reducer, it would average again. And this is different than taking the average of all the numbers in the first place. So what we can try instead is we define our combiner here. And now this does take the sum and the count, but emits both. So it's not taking the actual average. It's just doing the computation already for the reducer. The idea is the mapper stays the same, just emits the string and value pair. And now I'm building the sum and the counts, and I emit both as a pair. You see here, I emit the sum and the counts. And then the reducer gets these pairs and can go from there and actually compute the average here. Why doesn't that work? Yeah? The mapper is not producing the same result as the combiner. The signature is different. Just to verify this, think about what would happen if this combiner does not run. You said the combiner, there are cases where the combiner might not run at all. Then this mapper here emits string t and integer r, right? So no list. And the reducer here is expecting pairs of sums and counts. So that would clash. The moment the combiner doesn't run at all, I'm in trouble. Could also not run multiple times because it's expecting this list of only integer values, and it's emitting sum and count pairs. So this is just a good way to think if you want to make sure that your combiner is defined correctly. Like, these are the questions you should ask yourself. What happens if I do not run the combiner at all? Does my program still work? What happens if I run the combiner once? What happens if I run the combiner multiple times? And each 3 of these scenarios need to work. So here's the actual fix. Now we have the combiner as before, and the fix is already in the mapper now. We're emitting pairs, right? That's a fairly easy fix. I already know when I output the key value pair from the mapper that there was only one occurrence. So the count is 1, and the value is r, and then I omit this pair. Why does my pointer keep disappearing? You see that? Now it's the same signature. Now the mapper outputs pairs of values and counts, sum and counts. The count is always 1, and the sum is the actual value. The combiner runs, it produces sum and counts. So now we can do one additional thing. Oh, sorry, question?
Sorry. In terms of the value pair, can you just give an example of
When it wouldn't be 1.
So I guess, it's not specific to the mapper itself, but what type of function would you think where you'd be assigning value pairs that have different values?
Oh, you mean because for both, for the word count now it would be 1, and for the for this case it was also 1. Any other, for the anagrams it wasn't, right? In the anagrams, so the question was, do we have an example where the mapper does not output ones as values? And here in the anagram, it outputs the letters and the actual word. So this is the sorted version of all the letters in the word, and then you yield the word itself. So there is no restraint that this needs to be even an integer. So there's one other method that is even more efficient in a way, and that is in-mapper combining. So instead of caring about this combiner part, I just put this directly into the mapper function. So what I do is I keep track of a state that is internal to the mapper. So what you do here is an initialize function, and this creates 2 arrays, one for the sum and one for the counts. And now the actual mapper updates these data structures. So it's summing up the additional values it got, and it's keeping track of the count. So it's updating an internal status. And only when it's seen all the data it's going to see, then I have this close function, only then it starts to emit pairs. And now in these pairs, I can emit the actual states it had. Can you see the difference? The mapper before just output key value, key value, key value, key value. And then the combiner took care of this. And now we put it directly into the mapper. So this gives me more speed. Why? Why is this faster? What did I say costs the most? Yeah?
So there's no need for communication?
Yes. The need for communication is drastically reduced because now there's not even emittance. Before we emitted all the pairs and then the combiner took care of some of them. Now we're not even doing this anymore. The mapper internally already aggregates everything it computed and only then emits this one key value pair with the structure and the status. But you now need to keep track of your memory management, maybe. So because these structures here, right, each mapper now has an internal structure that it needs to save, and the structure can get quite large. If you do this for a word count example, and you need to have basically a cell, right, in your data matrix for every single word that is in your text, if the text is very large, this data structure can get really, really big. So, but this is what this looks like in Mr. Job. You can use this inside there. So I have, again, my class here. And this mapper, if false yield, this is, I actually don't know whether this is required anymore. I think somebody told me this is not up to date anymore. But I said the mapper normally needed to be a generator. This is a syntax trick to make Python believe that this is a generator, when in fact it's not doing anything. Right? If false, it's not ever going to be executed. So just for checking reasons, before the program actually starts to run, we trick Python into believing that this is a generator. And then it's the same as before here. For word and line split, right? I look at all the words in that line. But now, instead of emitting those pairs, I have my internal structure here, my local word count that was created up here, this init function. I created my local word count structure, and that is just a dictionary. So now I update this dictionary that the mapper has and count inside this dictionary at my word, I add the count for that word by 1. And only when the mapper has seen all the data it's going to see, then the framework runs mapper final, and this now yields the actual word and already the count of all the data that mapper has seen. So no need for combiners anymore. This is already the sum of all the counts. Is that clear? Understood? Explained enough? Questions? So for large dictionaries, I already said, which is better? Do you want to use a combiner or in mapper combining? What? The combiner, yes. Because of the memory problems. As I said, otherwise, if the dictionary gets really, really large, you need to store it in each mapper, and you might run out of memory. And for skewed word distributions, like you have a lot of words, some words are there a lot of times in your text, right? The and a are going to have a considerably higher count than supercalifragilisticexpialidocious. And then the in mapper reduces the load on the reducer very fast. So this is just something that took me hours, so I keep passing this knowledge on. This is a word of caution when you use this mapper final function. I have here an initial status inside my class, a test variable that is set to 1. Then I call the mapper. Inside the mapper, I set test to 2. And in mapper final, I just yield this test. And in the reducer, I have a standard error and write out this test function. And my surprise was that this test is going to be 1, although I set it to 2 in the mapper. So what happens here is we said the mapper maintains an internal status, like the dictionary we had before. And I just simplified the status to a single number and called it test. And I set it to 2 inside that mapper, so I updated the internal status. And this internal status is not normally what I thought is, this internal status is not inside the mapper, but it is an attribute of the class. So it should be preserved to the reducer, right? In normal object-oriented programming, if I define something like this, and I alter it in a function, I expect it to be altered for all the other functions that I call on this class as well. This is not the case. What the MapReduce framework does in the background is, after the whole mapping step, it destroys all the objects, and then the reducers are new objects. If there is no take-home message for you here, it's not that much of a problem, because most probably you won't run into this problem. If there is a take-home message, I hope I just saved you some hours of time. Questions? Yeah?
Yeah, sorry. Could you repeat that? So you said it destroys it at the reduce step, right? But you're already yielding it at the mapper final step. So when it's passing the 1 self.test at where the pointer is, it's saying yield 1, 1 there. That's weird.
Okay, so yes, this is, I did both here. So this yield here is going to work. This yield here yields self.test, and this is going to be 2 because I set it to 2 here. What I'm outputting here and what this 1 refers to is I'm just writing to the standard error here the actual value that is stored in self.test. This is not the value it got here that the reducer got up here. This yield here, this value here is going to be 2. Yeah. Running out of time. I'm just going to do PageRank because it's more fun. So I have one more. This is how to do graphs in MapReduce. It's just another example that I want you to see. I'm going to skip over all the math of PageRank. It's just fun for a fun way to see how graphs are transversed in MapReduce. So just think about you having a graph, right? And you have vertices and edges between those. And those give you connections in the graph. And they can be directed. So 1 is connected to 2 here. And these occur in all types of problems. You can think about finding the shortest path somewhere, or you can have social networks, or you want to find minimum spanning trees in some form of graph. So there's a lot of problems where you actually need to traverse graphs. And you need a representation for a graph in MapReduce to work with it. And one representation is an adjacency matrix. So this is what an adjacency matrix looks like. So you have 1, 2, 3, 4 here. Those are the different nodes in your graph. And then you have whether those are connected to each other. So 1 is connected to 2. And you can see here, there's my edge. So having a 1 at the entry ij means that there is a link from node I to node j. You can see I have my matrix here, but I'm wasting a lot of space because all the zeros in here basically do not provide any information. I'm not interested in nodes being not connected typically. So what I can do instead is I can represent them in an adjacency matrix, in an adjacency list. So you see this looks more efficient. I now have my node 1, and I just list all the nodes it's connected to. So it's giving me the same information as the matrix. It's just a different representation. So for each node, I now have a list with all the nodes it is connected to. And you can represent those in JSON. We already talked about JSON earlier. It's just a data format, right? Representing Python objects and lists and all of this in a string. So this is what it can look like. We have the node ID here, the node name, 1, 2, 3, 1, 2, 3. And now I have this adjacency list here. This is an internal counter. And then I say it's adjacent to node 2. And this edge has a weight now, and that is 10. This is how I represent the adjacency list in JSON. So I have my node 1, and it's connected to 2 with a weight of 10, and it's connected to 3 with a weight of 5. And if you do this in the Mr. Job, all you need to do is add this one line of code to your script. So I just want to do this briefly. So the PageRank is an idea to compute how important a website is. And Google uses a lot of more things as well, but this is part of their algorithm to rank websites. So the idea is that you start with an initial PageRank value for the page. And then each of these pages can contribute some credit to all the pages it is linked to. So there's an inherent importance to a page itself. And the idea is that if a very important page links to you, to your page, then this page must be important as well. Maybe not as important as the initial page, but it's going to be important as well. And then the target page just adds up all the credit it gets from outside pages, and that's its new internal value. And you iterate over that until you converge. So here you have an example of that. You have your nodes. These are web pages, right? And they have an internal state. And now what's it doing? It's kind of credit points that it can distribute to all the other pages it links to. And it says, I'm going to give credit to this guy, 0.1, and this guy, 0.1. What is happening is it's going out. It has an outward direction to 2 other pages. So it needs to divide its internal state by 2, and is passing half on to one page and half to the other. The idea is if one page links to a lot of other pages, you normalize over all the number of links. So you can see here now, this guy here, for example, got input from this guy and from this guy. So I'm aggregating a 0.1 and a 0.66 from this guy. So the new internal state is 0.166. So this is how you compute page rank. And then you iterate over this. Now the new internal state here is 0.166. And then again, it has 2 outputs, so it's half for each output. You aggregate all the different inputs you get from the different pages, and you update the status until you converge. And now we want to put this into MapReduce. And I'm only going to give you the color codes here. So in the mapping state, right, each of these nodes here has a mapper. And you can see it gets the node ID and this adjacency list that we talked about. This is node 1, and it's adjacent to node 2 and node 4. So it has this adjacency list. And this is what the mapper gets. And it's going to generate key value pairs for all the output, for all the credit points it sends out. So it's exactly the line of thought that we had in the example. So this outputs now literally sends the credit to node 2 and the credit to node 4. So it's going to output a key value pair with the ID of node 2 and the value of credit it gets from node 1. Right? We said node 2 gets credit from node 1. Here's the edge. So what the mapper does for node 1, it outputs the key value pair. Node 2 gets 0.1 points from me. And then in the reducer state, this is all sorted and summed up. So this is an idea how you can go over graphs with this adjacency list. Yeah, and you basically iterate over this until the values don't change. So you need to call MapReduce over and over again, right? So this is just one iteration, and then you need to start anew with the map. So this is actually something you need to take care about then yourself. You need to write a driver script that calls this MapReduce framework with the updated state again and again. Okay, I'm going to close with that. Do you have other questions about MapReduce? I know there was a lot of stuff that was very different from the other lectures. It was a lot of programming things. But playing around with this can be fun on your laptops at home. So I highly recommend that book in the beginning. Let me just put that on again. And then have a great day.